Hello, the topic of today's lecture is polygon triangulation. Let's start with one of the games that is implemented within the geometric game framework. Here you can see a dark room that is almost completely lit by two lights, but there's still some area that is in the shade. The rules of the game is that you need to place a certain number of lights to illuminate the whole area. So this game can be formulated as the art gallery problem, where we are asked to place a smallest number of cameras that will see the whole area of some art gallery that we represent as a polygon. So in the example on the right hand side, you can see that 5 cameras placed in these specific locations can see the whole interior of the polygon. For this lecture, we will make the assumption that the polygon describing the art gallery is simple. That means that there are no holes in the polygon and that it is described by n vertices. So let's define what we mean when we say a camera sees the interior of a polygon. We say that point P is visible from some point C. Both points lie inside the polygon if the segment CP completely lies within the polygon P. So here on the right hand side, P is visible from C because the green segment CP completely lies inside the polygon P, and P prime is not seen from C because the segment CP prime intersects the boundary of the polygon. For a single camera placed in some location inside a polygon, we can find all the points that are visible from the camera's location, and these points will form a so-called star-shaped region. The definition of a star-shaped region is exactly that it can be completely seen from one point. So now we want to minimize the number of cameras we need to use to survey the whole area of the art gallery. And of course, the number of cameras that we will have to use depends on the size of the polygon, on n, but also on the shape of the polygon. And in fact, it is an NP-hard problem, meaning that there is no efficient algorithm that can find the smallest number of cameras to survey the whole area of a given polygon. But what we can consider is some combinatorial bounds, simple upper and lower bounds needed to cover the whole area of the polygon. Trivially, we need at least one camera and at most n cameras, right? Because we can place a camera in each vertex of the polygon, and in this way we will definitely see the whole interior of the polygon. But are there any better bounds on the number of cameras that are needed and that are sufficient to survey any polygon of a given size n? To prove a given upper bound, we will try to prove that particularly many cameras always suffices for any polygon of a given size. And to prove a lower bound, we will try to construct a family of examples of polygons that require that many cameras to survey their interior. So let's try to find some better upper and lower bounds on the number of cameras that are needed for any polygon of size n. The first observation that we can make here is triangles are easy to guard. Indeed, if you place a camera in any point inside a triangle, it will completely see the whole interior of the triangle. So then a natural idea to place the guards inside a polygon is to partition the polygon into triangles and place a camera within each triangle. Now we have reduced the question to triangulating a given polygon. But that is, of course, if we can find such a triangulation. So I want to end this section with the following three questions. Does a triangulation always exist? Is it unique? And how many triangles does a triangulation have for a given polygon of size n? Well, in fact, the answer is yes, a triangulation always exists. It's not necessarily unique, but it will always consist of n-2 triangles if the size of a polygon is n. Let's try to prove this theorem. We're going to prove this by induction on n. We start with n equals 3, and for this case, the polygon is triangle itself. Trivially, it is already a triangulation consisting of 3 minus 2 equals 1 triangle. Okay, so the base case is trivial. Let's see how we can prove the induction step. Suppose we have a polygon of size n that is greater than 3. Then let's consider the leftmost vertex v, and let's denote its two neighbors u and w. Now let's consider the edge uw. There can be two cases. Either this edge is a diagonal in a polygon, meaning that this edge completely lies in the interior of the polygon. In this case, we can cut off this triangle UVW and reduce the size of the polygon, therefore completing the induction step. Okay, but what if UW is not a diagonal in the polygon? Well, that means that within triangle UVW, there may be other points of the polygon. We're going to find such a point T that is furthest away from UW, and this will ensure that the segment VT completely lies inside the polygon, and thus we can split the polygon into two smaller subpolygons. Indeed, we can partition the polygon along the diagonal VT into two smaller polygons of size m and n minus m plus 2. And after we apply the induction hypothesis to two smaller subpolygons, we get n minus 2 triangles. Okay, we have proven that a triangulation always exists, and it consists of n minus 2 triangles for a polygon of size n. But does the proof provide us with an algorithm? And if it does, what would be the running time of it? So take a moment to think about these two answers. Indeed, we can build a recursive algorithm based on the ideas of the proof, and the running time of the algorithm will be quadratic. Back to the art gallery problem. We have observed that guarding triangles is easy, and we have just proven that any polygon P can be triangulated into n minus 2 triangles if P has n vertices. So now we can simply triangulate the given polygon P and place a guard or a camera inside every triangle. This will give us n minus 2 cameras. However, we can reduce this number to about n over 2 cameras if we pair triangles in a smart way and place a camera on each edge joining each pair of triangles. We can further reduce the number of cameras needed if we consider so-called vertex guard, meaning cameras that are placed in the vertices of a polygon. So how many cameras are needed to guard a given polygon? Well, let's prove the following theorem, that n over 3 floor guards are sometimes necessary and always sufficient to guard a simple polygon with n vertices. What does it mean, sometimes necessary and always sufficient? Well, this is your upper and lower bound on the number of guards needed to guard any polygon of size n. Recall that to prove a lower bound, we want to construct a family of examples for arbitrary large n that will require, in this case, n over 3 cameras to guard them. So pause the video, take a few minutes, and see if you can come up with an example for arbitrary large n of a polygon that will require n/3 cameras to guard it. Okay, let's see if your examples are similar to mine. This polygon is called a comb polygon because of the spikes. If we count, we see that we spent 3 vertices for each spike. And indeed, we need to place a guard across each spike to see the tip of the spike. If we try to place a guard someplace in between the 2 spikes, it's not going to see the tips of the spikes. So we will need n/3 cameras to guard a polygon of this shape. Now, to prove the upper bound, we need to prove that n/3 guards are always sufficient to guard any polygon of size n. So to prove it, we're going to start with triangulating the polygon. The second step is to 3-color the vertices of the resulting triangulation. What do I mean by 3-coloring the vertices? We need to assign one of 3 colors to each vertex so that no edge has 2 incident vertices of the same color. In the figure on the right, you can see that all vertices are colored in 3 colors and none of the edge has 2 endpoints of the same color. How can we prove that this is always possible? Well, we can use induction, or we can consider a dual graph, which is a graph that has a node for each triangle in the triangulation, and 2 nodes are connected if the 2 corresponding triangles share an edge. The dual graph of a triangulation is a tree, and then we can traverse this tree and color the vertices of the triangles in the color so that no edge has 2 endpoints of the same color. Now, given that all vertices are colored in one of 3 colors, we can choose the smallest color class, and this smallest color class will have at most n/3 vertices. Thus, to find the placement of n/3 guards in a polygon of size n, what we do is first we compute the triangulation, we compute the dual graph of the triangulation, and we color the vertices of the triangulation by traversing the dual graph. And finally, we select the smallest color class to place the guards in it. This will guarantee that all triangles are covered by guards because every triangle has 3 vertices of different colors. So what is the running time of this algorithm? Well, we have said that we can find the triangulation with a quadratic running time algorithm. Then we can compute the dual graph and find the coloring of the vertices in linear time. So in total, we get a quadratic running time algorithm. The bottleneck here is, of course, computing the triangulation. So in the following, we're going to see how to improve the running time of a triangulation algorithm. We're going to build a faster triangulation algorithm using the following idea. We're going to partition the input polygon into simpler parts, and we're going to triangulate those parts individually. So what should these parts be? What polygons are easy to triangulate? We are going to use y-monotone polygons. So consider the following 2-step procedure. In step 1, we partition the polygon P into y-monotone subpolygons. A y-monotone polygon is such that any horizontal line intersecting it intersects it in one connected component. For example, the right polygon is not y-monotone because there exists a line L that intersects it in 2 components. On the other hand, the left polygon is y-monotone because any line intersecting it intersects it in one connected component. A useful property of a y-monotone polygon is that if we consider the top and the bottom vertex and we consider the boundary segments between these vertices, moving along these boundaries, we're always moving either up or down. After partitioning the input polygon into y-monotone pieces, we're going to triangulate each of those pieces separately. To subdivide a polygon into y-monotone pieces, we're going to classify the vertices of an input polygon into the following 5 types. The first 4 types will be so-called turn vertices. If we follow the boundary of a polygon, when we pass a turn vertex, we're going to change the vertical direction in which we move. For example, moving along the boundary in this direction, after passing this vertex, we change from moving downwards to moving upwards. So this vertex V is a turn vertex. So let's see what kind of vertices can be turn vertices. The first type of a turn vertex is a start vertex. If we sweep the polygon with a horizontal line, when it passes a start vertex, it's going to give rise to a new connected component. That is why it's called a start vertex. Geometrically, we can identify this vertex by considering the 2 incident edges if both of them are moving downwards from the vertex and the interior angle of the polygon is less than 180 degrees, then this is a start vertex. The next vertex is a split vertex. When we sweep over the split vertex with the horizontal line, the connected component gets split into 2. That is why it's called a split vertex. Locally, we can identify a split vertex again by considering the adjacent edges. Both of them need to be going down, but now the interior angle is greater than 180 degrees. Next, the end vertex is the symmetrical case of the start vertex. This is where the connected component on the sweep line, when passing the end vertex, terminates. Again, we can identify the end vertex locally by considering the incident edges. Both edges go upwards and the incident angle is less than 180 degrees. And finally, there is a merge vertex, which is the symmetric case of a split vertex. When a sweep line passes a merge vertex, the 2 connected components on the line merge into 1. The 2 incident edges to the vertex are going upwards, but the interior angle of the polygon is now greater than 180 degrees. Finally, there is a regular vertex. This is the vertex where the vertical direction of the boundary does not switch. Now we're going to prove the following lemma. If a polygon does not contain split and merge vertices, then it is y-monotone. To prove it, we're going to prove the contrapositive statement. Suppose the polygon P is not y-monotone. That means, by definition, there is a horizontal line L that intersects it in more than one connected component. So let's consider such a line L, and let's extend the boundary going through the point Q in this example until the next intersection with the line L. There can be 2 cases. In the first case, the boundary intersects the line L from top to bottom. Then we can consider the segment between the points Q and R and argue that there must be a split vertex on the segment of the boundary. In the second case, after extending the boundary, it intersects the line L from bottom to top. And in this case, there must be a merge vertex on the segment of the boundary between vertices Q and R. In both cases, we get either a split vertex or a merge vertex on the boundary of the polygon. Thus, if a polygon does not contain split and merge vertices, then it is y-monotone. This implies that if we want to partition a polygon into y-monotone components, then we want to get rid of the split and merge vertices by adding diagonals that partition them. But of course we need to be careful so that these diagonals that we add do not intersect the boundary of the polygon or each other. We are ready to present the algorithm to partition a polygon into y-monotone components. First, we're going to see how to add diagonals to get rid of the split vertices. We are going to do the following. For each vertex V, we are going to compute the edge of the boundary of the polygon that lies to the left of V. For example, in the figure on the right, 3 points of the polygon point to the same edge as their left edge. The idea is to connect the split vertex V to the lowest vertex W that is above V with the same left edge. So in the example on the right, W will be the lowest vertex that is pointing to left V. By inserting the diagonal VW, we're going to get rid of the split vertex V. To find such a vertex W, we're going to store a pointer called helper in every edge that will point to the lowest such vertex W. When a sweep line reaches the split vertex V, it will check which helper does the edge to the left of V has and insert the diagonal to that helper. And now we're going to see how to get rid of the merge vertices. When the merge vertex V is reached by the sweep line, we first update the helper of the edge to the left of V to set it to V itself. If the next vertex V prime reached by the sweep line is split vertex, then we simply add the diagonal V prime. If the next vertex reached V prime is on the right boundary, that means that the left edge will update its helper pointer to V prime, and we insert the diagonal V prime. And if V prime is on the left boundary, meaning that we have reached the endpoint of the edge left of V, then we simply connect V to V prime. Another way of dealing with merge vertices is to observe that if we rotate the polygon by 180 degrees, all merge vertices become split vertices, and we know how to deal with split vertices. To summarize, the events of our sweepline algorithm are given by the vertices of the polygon sorted by their y-coordinate. The status of the sweepline algorithm are all the components that the horizontal sweepline L intersects with all the pointers from the vertices to the left edges and with all the helper pointers stored in every edge. We are ready to put together all the observations made so far in a pseudocode. We're going to use a doubly connected edge list D for the output. We are going to populate the priority queue with the vertices of the polygon sorted by their y-coordinates. And we're going to use a binary search tree T as the status data structure. As we said before, we want to store each connected component in the status data structure. So we're gonna keep the left edges of each connected component in T. So now, while the priority queue is not empty, we're gonna extract the next vertex V, and we're going to handle it depending on its type. First, consider the case where V is a start vertex. Then we simply insert the left edge E into the status data structure, and we set V to be the helper of E. Next, if V is an end vertex, we want to check if the helper of the left edge E points to some merge vertex. If it is so, then we insert the diagonal from V to that merge vertex, and we delete E from the status data structure T. Now, if V is a split vertex, as said before, we're going to go through its left edge E and connect V by a diagonal to the helper of E. We then will insert the right edge E prime into the status structure T to designate the new component, and we're going to update the helper of E to be V, and we will set the helper of E prime to again point to V. If V is a merge vertex, then first we consider the right edge incident to V, and we check the helper of E. If it happens that the helper of E is a merge vertex, then we need to insert the diagonal from V to that helper of E, and we delete edge E from the status structure T. Next, we consider the left edge E prime of V, and we check what its helper is. Again, if its helper is a merge vertex, we're going to insert the diagonal connected to V. And next, we update the helper of E prime to now point to V. Finally, to process the regular vertex V, we're going to consider two cases, where V is on the left boundary and when V is on the right boundary. If V lies on the left boundary of the polygon, then denote E to be the top edge and E prime to be the bottom edge incident to V. And check whether the helper of E is some merge vertex. If indeed that is the case, we connect it to V by inserting a diagonal. We then delete E from the status structure T, we insert E prime into the status structure T, and we set V to be the helper of E prime. Now, if V is on the right boundary of the polygon, then we again check the left edge of V and check its helper. If the helper is a merge vertex, then we insert the diagonal connecting it to V, and we update the helper of the left edge E to now point to V. This finishes the algorithm to partition a polygon into y-monotone components. We now are going to analyze the described algorithm of partitioning a polygon into y-monotone components. First, we're going to prove the correctness. And to do so, we're going to prove that first, all the split and merge vertices are removed. And second, that we do not introduce any intersections by inserting the diagonals the way we do. The first claim is straightforward by construction. We need to check how we get rid of the split and the merge vertices. When we reach a split vertex, we add a diagonal going upwards from that vertex, and thus, indeed, the split vertex is removed. And a little bit more tricky, but we again can show that we get rid of all the merge vertices by connecting them with a diagonal that goes downwards from these merge vertices. To prove the second claim, we're just gonna do the case analysis. Consider the first case where V is a split vertex and V prime is the merge vertex, and we insert the diagonal V prime. Because V is the next event following the processing of the point V prime, trapezoidal area Q is empty, and thus inserting the diagonal V prime cannot introduce any crossings. The other cases are analogous. So now that we have proved the correctness of the algorithm, let us analyze its time and space complexity. Let's prove the following theorem. A simple polygon with n vertices can be partitioned in some time using some space into y-monotone polygons. So what is the time and the space requirements of the algorithm that we have just developed? Let's consider the steps that it takes. First, the algorithm creates the priority queue. Then it needs to initialize the status data structure. And then for each event, what it does is it deletes the next vertex from the queue. It needs to search, delete, and insert elements into the status data structure. And it will add at most 2 diagonals to the doubly connected edge list. If we use the min heap for the priority queue, initializing it takes linear time. Initializing the status data structure takes constant time because initially it will be empty. Now for the time that is spent for each event, the delete operation takes logarithmic time. The search, delete, and insert elements into the status structure also take logarithmic time, and adding at most 2 diagonals to the doubly connected edge list is constant in time. So in total, we spent logarithmic time per each event, and we know that there's going to be n events. Finally, for the space, the space will be linear. Is it easy to see? Well, we can charge each extra auxiliary variable that we use to the vertex or to the edge that it uses. And each vertex and each edge will only use constant number of those. So indeed, the space is going to be linear. So now we can fill in the blanks and say that a simple polygon with n vertices can be partitioned in n log n time using linear space into y-monotone polygons. Going back to our two-step procedure, step 1 was to partition a polygon into y-monotone subpolygons, and now we know how to do it. So now let's see how to implement step 2, which is triangulate each y-monotone subpolygon. Recall our observation that a boundary of a y-monotone polygon can be split by the topmost and the bottommost vertex into two monotone chains going from top to bottom. The approach here to triangulate a y-monotone polygon is going to be greedy. We're just going to stop from top to bottom and add the diagonals as we go. So let's start with the topmost vertex. Again, move down with a sweep line. And at the moment when we can insert diagonals to the previously covered vertices, we will do so. So how can we describe this process? What is the invariant here? Well, let's again repeat the few first steps of this sweepline process. We are covering the part of the polygon until we jump to the other side of the boundary to connect the diagonals. So until the first diagonal is inserted, the area that is covered by a sweep line is an upside down funnel shape. The property of the funnel shape is that the two chains on its two sides consist of concave vertices. Concave vertices are those whose measurement is greater than 180 degrees. And on the other side, convex vertices are those whose angle is less than 180 degrees. To be more precise, the funnel that we see when triangulating a y-monotone polygon is going to be of the following shape. It will have only one chain consisting of multiple vertices, and it will have one straight edge on the other side. As soon as we reach the end of this edge, we're going to start inserting the diagonals to the opposite side of the funnel. So this is a simple case of a funnel that we can see when triangulating the polygon. So let's see the full algorithm for triangulating a y-monotone polygon. The algorithm is the following. Again, consider the vertices of the polygon by the decreasing y-coordinate. We're going to initialize an empty stack and push the first two vertices in it. And then, for each next vertex, we are going to do the following. Let uj be the next vertex that we are going to process. And let's assume that uj and the vertex that lies in the top of the stack S lie on different sides of the boundary. Then, until stack S is not empty, we're going to pop each next vertex from it and connect to uj by a diagonal. This corresponds to the simple case that we considered in the previous slide. After we're done, we're going to push the previous vertex uj-1 and the current vertex uj into the stack. In the second case, where uj and the top vertex of the stack lie on the same side of the boundary, we are going to pop the vertices from the stack one by one, and we're going to insert the diagonals into the polygon, connecting the vertex from the stack to uj, as long as uj sees that vertex from the stack. As soon as we reach a vertex in the stack that uj does not see anymore, we push that vertex back into the stack, and then we insert uj into the stack. Finally, to process the last point un, we are going to connect it to all the vertices that are still in the stack, except for the first and the last. So this simple algorithm lets us triangulate a y-monotone polygon. So now question, what is its running time? The running time of the algorithm to triangulate a y-monotone polygon is indeed linear. Now we can join this result with the previous theorem that any simple polygon with n vertices can be partitioned in y-monotone polygons in n log n time using linear space. We can combine these two results into the following theorem. A simple polygon with n vertices can be triangulated in big O of n log n time using linear space. Question, does this result follow immediately? We are splitting a polygon into multiple y-monotone subpolygons, and each of them can take linear time to triangulate. Again, if we're doing counting carefully, we can charge each operation to a vertex or to an edge and show that each edge and each vertex gets charged only a constant number of operations. So indeed, the final result follows. To summarize, our two-step procedure was to partition a polygon into y-monotone subpolygons and then triangulate the y-monotone subpolygons that we have obtained in the first step. So now, if we want to go back to solving the art gallery problem, we can take triangulation, color the vertices, and find the n/3 guards to cover the polygon. So far we have considered simple polygons, but can we use the same algorithm to triangulate polygons with holes? Well, in fact, yes, we can triangulate a polygon using the same algorithm, but for polygons with holes, the art gallery theorem no longer holds. We can no longer expect to be able to cover a polygon with n/3 cameras. Instead, we can show that n plus h/3 cameras are sometimes needed and always sufficient if we have a polygon with n vertices and h holes. Now another question, can we find an even faster triangulation algorithm? And again, the answer is yes. Triangulation of a polygon has been an open problem for a really long time. Slowly, increasingly faster algorithms have been developed by the end of 1980s, but these algorithms were randomized. So far, we have considered only deterministic algorithms. Finally, in 1990, Bernard Chazelle published his famous algorithm of linear triangulation of a simple polygon. His algorithm is so complicated that nobody takes to implement it, and the constants hidden in the big O notation are so enormous that it would not be practical in any way. But for the analysis of the asymptotic running times, we can say that there exists a linear running time algorithm to triangulate a polygon. Later in this course, we may consider a much simpler algorithm that takes big O of n log star n running time to triangulate a polygon, where log star is an iterated logarithm. It is the number of times that you need to take the logarithm of n to get to the value that is less than 1.